I'm going to go through the practice test for the Unit 3 Organic Chemistry for Honors Chemistry, just question by question. And this one right below, you can sort of see here we have an oxygen atom, double bonded, and another oxygen atom. Okay, on this side over here, there's some carbon, so that would count as an R group. And here's some more carbon, so that would count as an R group. So we can see that this would be an ester. Question 1. Alkanes, alkenes, alkynes, or both alkanes and alkenes? So it has a molecular formula of CnH2n. Okay, that has to be an alkene. Answer B. And that's just because we learned those formulas. 2n, 2n plus 2, or 2n minus 2. Cis and trans only happens with double bonds. So that's also going to be answer B. Okay, you can rotate around the carbon-carbon bond. That is alkanes, all single bonds. Those can rotate. The others are stuck because of those springs in our models. Have a triple bond in the main carbon chain. Okay, a triple bond is what we see in the alkynes. Answer C. A bond angle of 120. Okay, bond angle of 120 is what we have when a carbon-carbon double bond. And so that would be an alkene. Answer B. C5H8 is an example. So we would look at the 8 and say, okay, is that double? Is that double plus 2 or double minus 2 for the 5? And we can see that's double 2n minus 2. So that would be an alkyne. Answer C. Are considered saturated. Okay, saturated, only the alkanes. Those are the ones that have as many hydrogens on as possible. So those are the answers for those. Ketone, amine, carboxylic acid, and an ether. Okay, has a carbon bonded to a nitrogen. Okay, the only one that has nitrogens in it is amine. So it's got to be answer B. Sour taste. Sour taste is classic for carboxylic acid. Answer C. Acetone. Okay, the "one" on there, that's the clue that it's a ketone. Answer A. And has a carbon bond that is bonded to oxygen only with a double bond. Okay, ether would have just a single bond. Okay, carboxylic acid would have a double bond and a single bond. Amine has nitrogens, so it must be ketone. Answer A. Has an oxygen single bonded to two carbons. That's an ether. Answer D. And vinegar is an example. Okay, vinegar is a carboxylic acid. Answer C. Now, these kind of problems, you take each one and say true and false, and then if the second statement explains the first statement, then we'll say correct explanation. So all bonds in C6H14 are single bonds. Okay, that 14 is double the 6 plus 2, so that is true. Organic compounds in the alkane family have a general formula of CnH2n plus 2. Now that is definitely true. So we can also say, yeah, this is a correct explanation, because we're saying in the alkane family is characterized by having all single bonds, and it does fit that formula, Cn2n plus 2. So since we know that C6H14 is an alkane, then we know, yes, it has all single bonds. Propanal and propanone are isomers of each other. Well, we need to draw these. So propanal is 3 carbons, and it has a double bonded O and an H. It's an aldehyde. And propanone is 3 carbons, and it has a double bonded O, but this one is in the middle somewhere. So we can see that this is still going to have the same formula. There's going to be 1, 2, 3, 4, 5, 6 hydrogens on each one, 3 carbons on each one, and an O. So those this is true, that they are isomers of each other. Because they both contain oxygen, no. Okay, they do both contain oxygen, but that's not why they are isomers of each other. They're isomers because they have the same molecular formula, but different structural formulas. So these two statements are true, but it is not CE. Last one, when 1 molecule of propane is burned, 5 molecules of oxygen is consumed. In a chemical reaction, matter is conserved. Okay, so I think both of these are true, and to really test that out, we need to write this out. Propane is C3, double the number plus 2, 8, mixed with oxygen. we can see we're going to get 3 CO2s, and we're going to get 4 H2Os. And when we add those up, that's 10 oxygens, so that's going to be 5 O2s. So the first statement is true, second statement is also true, but I don't think that that is a good enough answer. It's true, true, not necessarily correct explanation. Okay, 17. Which of the following elements has a bonding capacity of 2? We have to think back to our models, and the answer is oxygen. Oxygen has 2, hydrogen has 1, carbon has 4, chlorine has 1. So oxygen is the answer. Structural formulas differ from molecular formulas. Okay, molecular formula would be something like C3H8, but a structural formula would be showing, who is bonded to who, something like that. So it does show, structural formulas do show the arrangement of atoms, and it shows the bond angles in the molecule, not necessarily. The elements that make up the compound, okay, they both show that, so that's not good. And the number of each element present, that's true. Okay, so B almost caught my attention there, bond angles, but we don't necessarily draw these in the correct bond angles. Like we would draw this with 90 degrees, but we know the bond angles really are 109.5. So A is really the only good answer, the arrangement of atoms. 19, if you built a model of ethane, now ethane, we know ethane says it has all single bonds. How many sticks or bonds would you use? You can see what we do. We'd have 1, 2, 3, 4, 5, 6, and 7. We'd use 1 to connect them. So the answer here is C, 7. Number 20, which formula represents a member of the same hydrocarbon family as C4H18? So we'd say, okay, is that double? Double 8 is 16, and it's minus 2, so this is an alkyne. So we want to find somebody else, that is CnH2n minus 2. And so how about 4? 4 times 2 is 8 minus 2, so this could be the answer. In fact, that is the answer. Because this is 2n, and this is 2n plus 2, and the 4, 7, that's not going to happen at all. So answer A. How many isomers are there for the substituted hydrocarbon C2H4Cl2? Well, if we add these together, we get 6. So this is like C2H6, which means it's going to be all single bonds. All single bonds. So we start with this structure. Now we're going to put on chlorines. We could put 1 and 1, and we can have 1 and 2. Okay, so we have a 1,1 dichloroethane. We could have 1,2 dichloroethane. There's no cis and trans here because it's a single bond, so the answer has to be 2,2. We wouldn't have 2,2 because that would be the same as 1,1. Okay, which of the following is considered an isomer of 1,1 dichloroethane? Well, that's the one we just talked about here. So if I put a chlorine here and a chlorine here, that would be 1,1 dichloroethane. So what else could I have? Which can be considered isomer? 1,2 dichloroethane. That's the one we just did. So 1,1 dichloroethene. Okay, the fact that it's ethene, it would have a different formula. That's not good. Cis 1,2 dichloroethene, same thing. And dichloroethine. Okay, with the enes and the ines, we have a different formula. 23. How many carbons make up the parent chain in the following molecule? So we have to get used to kind of going around corners. And we can see we'd have 1, 2, 3, 4, 5, 6. And the answer is C. Now if we went further, which way should we start numbering them? It turns out in this case it doesn't matter because we have the dimethyl here, 2 methyls. And we could number from either side. It would be 3,4-dimethyl hexane. Okay, bond angle for this. So this little funny character over here, that is just an arrow. It just looks odd. And we can tell from where these are all single bonds, so all the bond angles are 109.5 degrees. Answer B. For 25, the chemical that was first really effective anesthesia. Okay, the anesthesia, that was the diethyl ether. And this you just know from the notes, and you're just memorizing the examples that we talked about. And so for ether, the really only famous ether is diethyl ether, the first really good painkiller for surgery. Now this molecule, we have a C double bond O connected to carbons on both sides. And so we can say, okay, this must be a ketone, and this is propanone. And in fact, this is the one we talked about in class as one of our examples, our main example, and that is acetone nail polish remover. Officially would be called propanone. The other three is all, those are all alcohols, and alcohols would be an O and an H. So if this came off O and then had a H, then that would be an alcohol, but that's not what this says. Which of the following is an isomer of this compound? So we have to look at this. What do we have? We have 3 carbons, and we have 1, 2, 3, 4, 5 hydrogens, and a Cl. So we need something that has that same formula, but it's a little different structure. So this one, we can say, no, that's not going to be the answer, because that's really exactly the same molecule as the original molecule. It's just been flipped around. So that's no good. Okay, this has all single bonds. That can't be the answer. Okay, below this we have CH3Cl. Again, that's exactly the same molecule as above. It's just flipped around. And I was wrong. Let's go back to this molecule. This is the answer. This one is the same as the one above, but this one is cis, whereas here we have trans. So answer A is the correct answer for this. D, we have the 2, so we have 1, 2, 3, 4 carbons on this one. That's why that D is not a good answer. So back here on A is the correct answer for this cis rather than the trans that was given. Correct name for this compound, we have to go for the longest chain. The longest chain is 3 in a row with one coming off the side. So this is a methyl on a propane. So it's going to be methylpropane, answer D. Now officially you could call that 2-methylpropane, but there is no such thing as 1-methylpropane or 3-methylpropane, so the 2 is actually optional. So methylpropane is the correct answer. If we were going to burn some propane, okay, burn any kind of a carbon-hydrogen compound, we mix it with oxygen and we turn into CO2 gas and H2O. So which of the following are products? CO2, H2O, not ester. So 1 and 2 only, answer C. 30. When the above compounds are combined, okay, what happens? Well, you can see we have a C double bond O, OH, that's an acid, and we have an OH, that is an alcohol. So when we put these together, we're going to take the OH here, and remember from the alcohol, we're going to take the H that's connected to the O, those two form water, and the other two pieces we would have to put together will get an ester. So when these are combined, an ester forms, that's good. The product may have a nice smell, that's classic for esters, and a water molecule is produced, that's true. So the answer is 1, 2, and 3, all those are true. For 31, how many oxygen molecules are required to completely burn 1 molecule of ethanol? So you can see what we have C2H5OH, and we're going to think of that as 6 H's and O. Okay, we had to mix with oxygen. We're going to form 2 CO2s, and we can have 6 hydrogens, so that's going to be 3 H2Os. And what will happen is we have 2 times 2, we have 4 oxygens here, 3 times 1, 3 oxygens here. So we have 7 oxygens on the product side. That means we have to have 7 here on the reactant side. Here's 1 in the alcohol, and this must be the other 6. So that's going to be 3 O2s. So how many oxygen molecules are required? Okay, the answer is 3. 3 oxygen molecules to burn the ethanol. 32, the following polymers. Now, real quickly, this is not going to be on the test. We were talking about polymers because you ought to know about polymers. That was derived from which of the following monomers. So what we do is we would look at these and see that this is kind of repeating here and here and here and here and here. So each of these little pieces would look like the original monomer, but we'd have a double bond in between. So we're looking for a molecule that's double bonded, and it has a H and a H and a Cl and a Cl, and that's not A because it has single bond. This looks good. Okay, here there's too many carbons, and this only has one Cl, so that cannot be the answer. So the answer there is B. Now complete the following table. Now, this question here is a chart, and the chart is over 2 pages. And also, in Mr. Grove's class, the practice test that I gave out apparently had a missing page, so be sure and look at the version online. But here's a molecular formula, C3H4. So the first thing we say is, okay, is that hydrogen number double the carbon number? And no, that would be 6, so this must be 2n minus 2. So that tells us an alkyne, and with 3 carbons, the name of this is going to be propyne. Now, how do we draw that? We're going to say 3 carbons. We're going to put a triple bond, and now the important part is to go back. So this bonding here, we'll have another bond here between the 2 carbons. So what else can we do? On this first carbon, we have 1, 2, 3, so we can have one more hydrogen. On the second one, we already have 4 bonds, and the last carbon, we have 1, so we can add 3 more. So that would be our formula. There would be H's on the end of each of those red ones. Okay, for the second one, we have the formula 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons altogether, so it's C8. We can see that everything is a single bond, so the hydrogen number is going to be double the number plus 2. So double 8 is 16 plus 2, that'll be 18. So C8H18. Now to name this, we have to go back and find the longest chain. We can kind of see the longest chain goes around the corner. And that's 1, 2, 3, 4, 5, 6, 7. So we're talking about a heptane with a methyl hanging on carbon number 2. We'd want to start numbering from the left. So this would be 2-methyl heptane. Now this will really be one big long word, but I'm not going to fit it on my screen. So 2-methyl heptane. Now moving down, just to be on the next page, trans 1,2-difluoroethene. So it might be easier to draw that first. So the difluoroethene, okay, we have 2 carbons and a double bond, and I like to draw them with the 120-degree angles. 1,2-difluoro, that means we go to fluorine on the first carbon and a fluorine on the second carbon, but the trans tells us that one fluorine goes up and one fluorine goes down, and the other 2 sides would be hydrogens. So we can see the formula would be C2H2F2. Now on this one here, we say we have 1, 2, 3, 4 carbons in a row. And we have a chlorine, we have a chlorine, and we have a chlorine, and the rest are hydrogens. So the formula would be C4H, what do we do? 1, 2, 3, 4, 5, 6, 7, and Cl3. We always put the C's, then the H's, and then anything else afterwards. Now, what about the name of this? We would have 3 or 4 in a row, so that's a butane. And we can see that there's more chlorines on the left than on the right, so we're going to start numbering from the left. So this is going to be 1, 1, 3, trichloro, and then continuing the next line, butane, since it's all single bonds. So 1, 1, 3, trichlorobutane. Okay, 2-pentene. Well, the pent part tells us there are 5 carbons. Now the ene means there's a double bond, and the 2 says it starts on carbon number 2. Now we're going to go back and just finish up, put all our hydrogens on. So the first one has room for 3 more hydrogens. Second carbon already has 3 bonds, so we'll put 1. Third one has 3 bonds, so we'll put 1. And then you can see we put 2 more bonds and 3 more bonds. So you can see what's happening here is that we would actually have a cis and a trans version of this 2-pentene, and we would accept either picture. Now how do we do this? Is C5, and since it's an ene, it's going to be double the number, so C5H10. Now the last one, butanoic acid. Butanoic acid. So we know the acid means C double bond O, O and H. And the butanoic part means 4 carbons all together. So we have 4 carbons total, C with a COOH group. We'll go back and put some hydrogens in, and that would be our butanoic acid. We're going to get our formula, C4, H1, 2, 3, 4, 5, 6, 7, 8, O2, or a lot of times we would go from left to right, and we might say something like C3, H, 1, 2, 3, 4, 5, 6, 7, C3, H7, COOH, and that would give clues to the person who's looking at it that this is a carboxylic acid. For question 34, it says draw and name an isomer of the compound in 33B. So I recopied that question up there. And that one, you remember, was 1, 2, 3, 4, 5, 6, 7. It was a 2-methylheptane. So there are a lot of different things you could do. There are 8 carbons altogether. So you could just do 8 carbons in a row and call this octane. When we put the hydrogens on, that would be a fine formula. Here we have 2-methyl heptane. We could make a 3-methylheptane, just hook it to the 3rd carbon. We could make many, many different molecules that are possible, but they should have the formula C8H18 in order to be true. Now on question 35, it's a similar sort of a question, saying you want some kind of an isomer for the compound that was in 33D, and that's this molecule. And this, we have 4 carbons, and we have 3 chlorines. So we could draw these in several different ways. Okay, we could have 4 carbons and maybe go 1, 1, 2, or we could go 1, 2, 3. So I'll do that. So I'm just going to say 4 carbons in a row. And we'll put all of our hydrogens on. And on 3 of those places we'll put a chlorine, so I could put it 1, 2, and 3. And I would call this 1, 2, 1, 2, 3 dash trichloro butane. And there would be many, many different answers for this same question. Now in this one, a little bit different, asking you to identify the different functional groups. So we can see that this guy here, that's a benzene ring. B-E-N-Z-E-N-E. Okay, up here we have a C double bond O, and then we have a single bond O, and on the single bonded O is what we care about, that's the H. So we know that that is a carboxylic acid. Now if that was some more carbons right here, then we would know that that is an ester, but this is a carboxylic acid. And the last one, we have C double bond O, single bond O, and that one is connected to more carbons, so this one is an ester. So the 3 answers: carboxylic acid, ester, and a benzene ring. For 37, draw the products that are formed when you put these 2 together. So here from our acid, the COOH, we're going to take the O and the H. From over here where it's the alcohol, the O and the H, we're going to take that H. So we're asking for the products, so we're going to form water. And then the other parts are going to go together, so we'll just try this. So we're going to put a carbon with 3 hydrogens, then another carbon, double bonded O, so I'm doing this stuff. Then we jump all the way over to this oxygen. So we get an oxygen, and we have 3 carbons, one going up, one going down, and we need to put a hydrogen on this carbon, and 3 hydrogens here, 3 hydrogens here. So it's a little bit messy, but that would be the answer, and that would be an ester. So notice again, from the COOH group, you want to take the OH. From the alcohol group, you want the hydrogen. Now we also did something like this with proteins where this was an amine, so we would have taken the hydrogen off of the nitrogen, but if this is an alcohol, we take the hydrogen from the oxygen. Number 38, write the balanced equation for the combustion of pentanoic acid. So we say C5, H10, O2. Notice that we have some oxygens here. That's going to make a difference. Add it to O2, and we're going to get CO2. We have 5 carbons, so we're going to have 5 CO2s. We have 10 hydrogens, so we're going to get 5 H2Os. And we're going to add up our oxygens, so I'll change colors. So here we have 5 times 2, we have 10 oxygen atoms here. 5 times 1, 5 oxygen atoms. So altogether we have 15 oxygen atoms on the right. So we need to have 15 oxygen atoms on the left. So here we have 2. That means this is going to be 13. And we could write that as 13 over 2. So our balanced equation could be 1 C5H10O2 plus 13 halves O2 turns into 5 CO2s and 5 H2Os. And it might be just better to go back and just double everything. And then what we'd say on here is 2 C5H10O2s plus 13 O2s turn into 10 CO2s and 10 H2Os. Now either of these are great answers, but on a test a lot of times it'll say give your answer using whole number coefficients, in which case the second answer is the one you would want. Now the last few questions, some numerical ones. It says a 3.37 gram sample of an unknown gaseous alkene, that's a clue, occupies 2.69 liters at STP. So we have 3.37 grams. Find the molar mass of this compound. Well, molar mass is grams per mole. Grams per mole. Let the units guide you. So we have 3.37 grams, but we don't know moles, but we do know that it's 2.69 liters. And we know from our old mole map that we can change liters into moles. And remember that 1 mole is 22.4 liters. So if we do that much, then we find out that this is going to weigh 28.1 grams per liter. Now, it actually comes out to 28.06, but this is good. Now you can also go ahead and just take your 2.69 liters, change it to moles, then take 3.37 grams divided by 0.120 moles, and you get the 28.1 grams per liter. Grams per mole, excuse me. Okay, so that's our answer. Okay, B, find the molecular formula for this compound. Well, one of the clues is that this is an alkene, so we know it's CnH2n. So now we can already just go ahead and guess. We know that it could be C2H4, or it could be C3H6, or it could be C4H8. And we say, well, let's start off here. That's going to be 24, 2 times 12 plus 4. That's 28. So we know that this is the formula right away, just by trial and error. These are going to be too heavy. So the molecular formula C2H4. Now find the number of molecules in this compound. Well, if we had the liters, since we know the, we can go from the liters, or we can also go from the grams, and we can just try the liters. So 2.69 liters. Now from our mole map, we want to go liters to molecules. It's going to take 2 steps. So we know that there's 22.4 liters in 1 mole. And remember that 1 mole is 6.02 times 10 to the 23rd molecules. And if we work this out, we get 7.23